Hi, welcome to this course on computational mathematics with Sage Math. We are looking at solving linear programming problems using Sage Math, and this is third lecture in linear programming problems. So in the last two lectures, we looked at several examples of linear programming problems, including its formulation, and we also looked at how to solve linear programming problems in two variables using graphical method. Now in this lecture, we are going to look at some definitions and few results. We will not be proving these results. For proof of these results, one can refer to some standard text on operation research. I have already given you some references in the first lecture. Right, so let us get started. So this is what we are considering as the standard linear programming problem, which is of minimization type, subject to this equality constraint x equal to b, where x is non-negative and the right hand side b is also non-negative. We are also making the assumption that this matrix A is of full rank. Now solving this linear programming problem is all about solving this system Ax equal to b, and we have to look at only those solutions of Ax equal to b which are non-negative. Right. So as I said, we are making this assumption that rank of A is M. Let us also write A as column matrix A1, A2, An. So A1 is the first column of A, A2 is second column of A, and so on. And the number of constraints is less than equal to number of variables. That means so that it may have infinitely many solutions. This system Ax equal to b will have infinitely many solutions. Now this x is a column vector x1, x2, xn, and b is also a column vector b1, b2, bm. We are assuming that b is also non-negative, that is all all this b1, b2, bm are non-negative. And let us further assume that the rank of A is m, that is A is of full rank matrix, and since the rank of A is m, that means the A will have some m linearly independent columns. Let us assume that the first m columns of A are linearly independent in the sense that A1, A2, Am forms a basis of Rn. In case not the first m are linearly independent, of course we know that some m are linearly independent, so we can always interchange the variables and then we can bring them to the first m linearly, to the first m columns. Okay, so there is no harm in assuming that A has first m linearly independent columns. Right. Now let us look at this set which we defined earlier. Omega, which is set of all x in Rn satisfying the constraints, that is x equal to b and x non-negative. Any point in omega is called feasible point, and omega itself is called feasible set. And one can show that this omega is a convex set. What do I mean by that? It means that if you take any 2 points inside omega, then the line segment joining those 2 points will also lie inside omega itself. So any such set is called convex set, and omega one can show that this is always a convex set. It is quite easy to prove. Let us look at further. So as we said that we have assumed that rank of A is m and first m columns of A are linearly independent. So if I look at this sub matrix of A by taking first m rows and m columns, let us denote this by A suffix b, then this matrix will be m cross m matrix, and since its rank is going to be m, this is going to be non-singular, it is going to be invertible. And if it is invertible, then let us write AB inverse b. B is the right hand side. This makes sense because AB is m cross m, B is m cross 1, therefore AB inverse b makes sense, and let us write this AB inverse b is equal to xb. Now this xb is nothing but it is a solution of ab times x is equal to b. Now xb has m components. So if you write remaining n minus 1 components of in this xb as 0, then this x will be what? It will be x1, x2, xm, comma 0, 0, 0. So, and that is what is called basic solution of this standard linear programming problem. This is called basic solution. So what is basic solution? It is just obtain xb, which is ab inverse b, and then to this append the remaining n minus m components or coordinates as 0. In case if you don't have first m columns linearly independent, then you just select those columns of A which are linearly independent, call them as AB, and then find xb is equal to AB inverse B, and then the remaining components of x, so there will be remaining n minus m components. Those components you substitute as 0. That is what is called basic solution of standard LPB. Now remember we wanted x to be non-negative. That means all x should be non-negative. At present x we have got as a basic solution, which is nothing but solution of ax equal to b. But in case all the components of x, that is all the components of basic solution are non-negative, then such a solution is called basic feasible solution, in short BFS. And the variables corresponding to basic solution, that is in this case as per our assumption it will be x1, x2, xm, they are called basic variables, and the remaining variables are called non-basic variables. Next, let us look at in case we have some component of this basic variable as 0. In particular, in case you have a basic solution in which some of the component with respect to basic variable is 0, then such a solution is called degenerate basic solution. And in case you have basic feasible solution which is degenerate, that means some component of basic variables are 0, then we say that that is a degenerate basic feasible solution. Now let us look at, if as I said, this omega is a convex set. So if you look at this omega, this is let us say this is the feasible set of this given linear programming problem. These corner points, these are the corner points. One can define these corner points are the points x, such that x cannot be written as t times x1 plus 1 minus t times x2 for some t strictly between 0 and 1, and for 2 points x1, x2 inside omega, right? So what it says that if I have this is a corner point, I cannot write this as a strict convex linear combination of 2 points from this omega. Such points are called corner points. For example, if I look at any point on this line segment joining this point and this point, I can always write as a convex linear combination of this point and this point. Similarly, the interior point also we can write. Right. So actually solving linear programming problem is all about finding these corner points. Now let us look at, if we have any feasible solution x which yields the minimum value of the objective function, then we call that solution as optimal feasible solution. And in case you have an optimal feasible solution which is also basic, then we call that as optimal basic feasible solution. So solving linear programming problem is all about finding optimal basic feasible solutions. Right. Now let us look at couple of results. First result is called fundamental theorem of LPP, and this states as follows: given any linear programming problem, the following are true. What are they? The first one, if there is a feasible solution, then there is a basic feasible solution. So it says that if you can find a feasible solution, find a feasible solution is same as saying the omega is non-empty. So in case omega is non-empty, you can find a basic feasible solution. That means you can find a solution in which all the components are non-negative. Second part of this theorem says that if there is an optimal feasible solution, then there is a optimal basic feasible solution. So that is what is called fundamental theorem of linear programming problem. The second result says that the extreme points of this omega, which is a convex set, are essentially the basic feasible solutions, right? So that is same as saying, in case we want to solve this linear programming problem in standard form, all we need to do is we need to find these extreme points. So these extreme points are essentially the basic feasible solution. In fact, it is if and only if, right? So x star, a point in Rn, is a basic feasible solution of x equal to b, x non-negative, if and only if x star is an extreme point. Okay. So this second result tells me that if I have to solve this linear programming problem, all we need to do is we need to find all these corner points or extreme points, and that's exactly what we did in case we solved the problem using graphical method. We found out all those corner points, and those corner points, at those corner points we evaluated the objective function value, and we choose one which takes maximum value in case of maximization problem and minimum value in case of minimization problem, right? So these two are very important results as far as solving linear programming problems are concerned. Now let us look at how to find basic feasible solutions. So let us take some example. The first example is this. Find out basic feasible solutions, rather all basic feasible solutions of these two equations, 2x1 plus 6x2 plus 2x3 plus x4 is equal to 3, and 6x1 plus 4x2 plus 4x3 plus 6x4 is equal to 2. All x1, x2, x3, x4 are non-negative. So how we are going to find all the basic feasible solutions? So if you look at this set of equations, I can write this as Ax equal to b. Now A is going to be 2 cross 4 matrix, and it is easy to check that this matrix A has rank 2. So this is a full rank matrix. Now you have to choose some two columns which are linearly independent, right? And then call that as AB, and then find AB inverse times B. In case all those components are non-negative, then we will append the other two coordinates as 0, and that will give me the basic feasible solution. So let us see how we are going to implement this in Sage. So first let us define this matrix A, which is the first row is 2, 6, 2, 1, second row is 6, 4, 4, 6, and then let us write the right hand side as a vector B, and let us find the augmented matrix of the system. That means A dot augment B and subdivide equal to true, and let us apply RREF to this augmented matrix. This is how we solve the system of linear equations. So you can see that this is the augmented matrix of the original system. This is the augmented matrix, also known as canonical form of this augmented matrix. So in this case, if I look at the set of equations represented by these two, the original system was this, and the second, which is represented by this RREF, this is given by x1 plus 4 by 7 times x3. So that's what you have, x1 times 4 by 7 times x3 plus 8 by 7 times x4 is equal to 0, and in this case x2 plus 1 by 7 times x3 minus 3 by 14 times x4 is equal to half. So you can see here this 0 comma half is one of the solution. Now we need to look at how to find these basic solutions. So for this I have written a small code, Python code. So first what we are doing, let us write n as number of columns. In this case it is 4, and extract all the columns of A in small a, and let us create a list of basic feasible solutions. To begin with, it is empty list. Now what we are going to do, we will choose two columns, let us say I and j, such that I is strictly less than j. And then we will start with a basic solution which will be 0, 0, 0, 0. So it will be a list containing 4 elements and all of them is 0. And then what do? We extract ith column and jth column of A and create a column matrix, let us say M. And in case this matrix is invertible, that is same as saying AI comma AJ will be linearly independent. If that happens, then write the solution, that is S is equal to solve mx is equal to b, right? This is solution of nothing but mx equal to b. Here m is nothing but your ab in case the ai and aj are linearly independent, right? So and then the ith component of bs, which are all 0 at present, write as s of 0, the first component of the solution, and jth component of bs, which is 0 at present, replace it by second component of s. And let me not print this here, let me exclude this print so that you don't get confused. And then let us check whether this solution which we have got have all non-negative components. That is, if s of 0 is non-negative and also s of 1 is non-negative, then what we get is this bs will become basic feasible solution, otherwise it is not going to be basic feasible solution. And in case it is basic feasible solution, then you append it into the list of basic feasible solution. But it is likely, it is possible that when you take I and j, different set of I and j, the original, the solution, which basic feasible solution which you get has already appeared before. That is why you append only when the new basic feasible solution, new basic solution is going to be different from the one which is already taken. Okay, so let us run this code, and when you run this code, you can see here the first one, we have taken the first column and second column, and in this case we got the solution as 0, half, and this is a basic solution because all the components are 0. And also this is respect to x1, this is respect to x2, this is respect to x3, this is respect to x4. So this x1 and x2 are linearly independent, but x1 value is 0. So this is a degenerate solution, right? Similarly, if I take 0th column, that is the first component, first column, and the third column, then the solution which we get, this is 2 minus 2 7 by 2, which is not basic because the first component is negative, right? So this is not taken. Similarly, if I take 0, 3, that is first column and the last column, then also this is not feasible. Then next go to I equal to 1 and j equal to 2, that is, so first column and second column and third column. In that case, the x2 value is half, x3 value is 0, and therefore the solution is 0, half, 0, 0. But that has already appeared here as a basic solution, so it will not get appended again, right? Similarly, do the other things, and in this case, what we find is that though there are 3 set of columns which are linearly independent, the 3 set of 2 columns which are linearly independent. One is first column, second column. The second one is let us say second column and fourth column, and the third one is there are the 3 of them, namely one is first and second. This is basic. Then you have first, second column and third column, and then you have second column and fourth column. But these all these 3 results in the same solution, namely 0, half, 0, 0. So there is only one solution in this case. There is only one basic feasible solution in this case, and it is in fact degenerate basic feasible solution. Let us take another example. So this example, this is here 3 cross 4 matrix. So find all basic feasible solutions of Ax equal to b, x non-negative, where A is given by this 3 cross 5 matrix and B is 3 cross 1 matrix. So again we will do exactly the similar thing. First, let us augment this matrix, augment this B in A, and when you apply RREF to this, then you see here first three columns are linearly independent. That means this system will have infinitely many solutions. And in fact, this last column, that is 22 by 9, 1 by 9, minus 22 by 9, minus 29 by 9 is a solution of this system, but this is not basic actually. So this simply means that in case we take first three components, first three columns of A, this is not a basic feasible solution. Now let us write a program for the same thing. So again we will write n as the number of columns of A as the columns of A, and this time we have to take three columns. That means we will run a nested loop with I, j and k, and we will take I, j which is strictly greater than I and k which is strictly greater than j. So therefore I, j, k will be distinct, and again exactly the same thing. Instead of in the previous one we had I and j varying, now I have I, j and k varying, right? So the code is exactly similar except you have extra component for third column, right? So let us run this, and when we run this you can see here in this case 0, 1, 2, that is the first three columns are linearly independent. However, this is not a basic feasible solution because this component is 0. If I take first, second and the fourth column, then again this is not a basic feasible solution. If I take first column, second column and fifth column, then this is first column, second column and fifth column, then this is a basic feasible solution, and similarly the other things. So if you look at this, there are four basic solutions in this case, basic feasible solutions in this case, 1, 2, 3 and 4. So we have obtained all basic feasible solutions in this case. Of course, if you have larger matrix, there will be many basic feasible solutions. In fact, if m is very large and so is n, the number of basic feasible solutions could be as many as n choose m, which is quite large in case m and n are large. So it is practically impossible to find all basic feasible solutions. So therefore, if I want to solve this linear programming problem using brute force method, that is find all basic feasible solutions and then find the value of objective function at all those basic feasible solutions, and then compare all these values and then choose one which gives me the smallest or the maximum, will be very, very time consuming. That is why you need a systematic method of solving linear programming problem, so that you don't have to go through finding entire basic feasible solutions. Okay, so let me leave you with a couple of simple exercises. So find all basic feasible solutions of this and this. They are the three problems. So you can make use of the codes which I have given here, and then you can find all these things. Of course, you can also modify these codes, and you can create some other procedure to find all basic feasible solutions. Okay, so thank you very much. In the next lecture, we will look at how to develop methods for simplex method, right? We will look at basics of simplex method or theory behind simplex method, and that is actually applying row reduced echelon form to this matrix Ax equal to B, or the system Ax equal to B. So we'll see that in next class. Thank you very much.